All right, podcast. Um, recording and it are there with parts. Let me go and get back to the session that I was in before, which is not this one, but the so learning about PC design. It's PC PCB design with Grok 420 beta. Okay, guys. So what I've done is the following, right? So I have now swapped model behind for Grok 4.20. Okay. And if you've been following some of the past, some of the previous streams, you will notice the difference. So let's go back to where we were. We are here at the task. We're here at the second step, the plan, right? And I'm gonna time box this to 30 minutes, and because I have to finish a few other things. There's a few big announcements coming, but I still want to do that. So I'm recording it for YouTube as well, and let's get started. Let's get started. So draw a simple PCB diagram. Components placed to minimize crosstalk, labeling potential sources of interference. Okay. Yeah, perfect. Let's do these. So let's get started. So draw a simple diagram of PCB with components placed to minimize crosstalk labeling. I mean, again, what are ways to minimize this? So we have to draw something, right? We have to go to the canvas and draw something, but let's just go back to guys, maybe I just came out with another little feature. Sorry. I think there might be a nice way it was like maximize the tool or something like minimize monitoring. You know what I mean? Minimize monitoring. That would be a nice feature. Anyway, so beyond simple diagram of PCB with components placed to minimize crosstalk label. Crosstalk. I mean, it's a little. I'm missing a bit of context, I guess. So let's start from here. So where should we? Let's just mark this one. Where should we position power supply? Where should we position a microprocessor? So we have a few tasks in here. And how should I place the ground plane to minimize crowd? This is an interesting discussion because, to be honest, I didn't know that there were different ways to place the ground plane. Let's ask: are there different ways to place the ground plane? First of all, you notice how fast it is. It's much faster than Open Router before. And yes, there are several approaches. What factors do you think should guide your choice of ground plane style? Okay, by that style, solid, copper, split planes. But here's like, should I place the ground? How should I place the ground? He was suggesting materials rather than configuration. So maybe this is just badly phrased. Layout configuration, dedicate layers versus cores. Oh, okay. How do you think the number of layers in a board influences ground plane placement? So do you mean in the sense that it's like sandwiched? On an outer layer. Okay, yeah, sure, fine. So And we'll place the ground plane to minimize crosstalk from noisy components. I mean, that's actually not bad. It could be that one way is basically to do this, so to just place it in the middle. I don't think how else would you be able to put a ground plane. Although the ground plane goes on top of the. Wait. We're talking about the ground plane. We're talking about the ground plane actually. We're not talking about the what's it called? The solid base. We're talking about the ground plane. So the main purpose of the ground plane is basically to help drain electricity, right? Not sure. Help me out a bit, please. Maybe I have to fine tune the prompt a bit. I want the assistant to give me answers. Actually, consider the path return. Consider the path return current takes after leaving a signal tray. How might a solid ground plane help with that flow? Okay. Noise and loop area. What is a loop area? A lot of different new concepts. But now I guess. But back where? About the path the signal takes outbound and its return path back to ground. I mean, but a path goes from component to component, right? Why does it need to go back? Current must form a closed loop to flow. Yeah, well, okay, that's true. That's a stupid question I had. So in a PCB diagram, how should I place the ground plane to minimize crosstalk from noisy component? Oh. So I guess one way. So this question is very open, right? Because we're so again, could it be that so could it be that the ground plane is, for example, not underneath the components? You know what I mean? Could it be okay, so there's a suggestion in your PCB diagram. Try placing a continuous ground plane on a dedicated layer beneath the signal traces to shield against crosstalk from noisy components. How is it interference? Why would it actually? Are ground planes always continue? And why would a ground plane help shield? Why would a ground plane help shield plane and the layer beneath crosstalk from crosstalk from components? What problems could gaps create or return for return currents? When nearby ground plane affect electric fields from noisy components? Those are good questions, man. So I like the way the assistant kind of operates. Although I'd like to get more answers from it. But that's good because it kind of comes back with with follow-up questions, but that's a good one. It's first of all, we need to understand. Okay, so first of all, I think we just need to understand. We need to understand crosstalk better. I mean, we did do that in the previous session, so I know what crosstalk is, but it's like type of happening. Signal trace shield against crosstalk. So would it shield it because it maybe has some negative effect, like a negative? Because it's returning, generates the opposite magnetic field, something like this. Could it be? So, you know what I mean? I mean, that is maybe not a bad thing. So, let's say if I'm having my path, I'm drawing the board now like these. And if I have my electrical path here, and the ground, the green, the ground is here, right? I guess what's happening is it's just a guess, okay? So is it true, or can it be that just checking, okay? I'm still testing for quality. So can it be that the electromagnetic field from the signal path and the one from the ground plane sort of fear/cancel? Fields interact when the return current flows in the ground plane directly under the signal. How might their magnetic fields affect each other? But then that's simple, right? Then essentially, I would say that's fine. Using a canvas tool to draw a simple diagram of PCB with components placed to minimize crosstalk, labeling potential sources of interference, such as close proximity between noisy and sensitive traces. Where should I position the power supply component away from signal traces in my PCB? I mean, the few tasks. So on one side, we have the power supply, and on the other side, we have the microprocessor. Okay, so do individual components have specific noise profiles, like the power supply and a microprocessor? Do they have a radius where noise is more intense? Because I think that's a good question. The noise intensity decreases. Yeah, so I think so. I mean, I think maybe that is why. So we've got the power supply, the microprocessor. I need to find a way to squeeze still state here, because I want to see all the I like to see all the questions at a glance. Those get a little tricky. The ground plane. Okay, so we actually have a bunch of clues in here. Signal proximity and ground planes when thinking about optimal component placement to reduce crosstalk. Well, let's try to do this. So the way that I would do this The way that I would do this is very simple. It's basically, I would say, on one side, so if this is the base of the PCB, then I would put actually the ground plane here. I think then there needs to be some sort of isolation or something like this in here. Yeah, and then the actual like paths maybe go on top or something like this, right? And here we have the paths. So these essentially, that's one aspect of the drawing, right? We have what we have in this case is here. Are we having the same problem with the? Okay, so we have we have we have what did we say? So the blue, no, the blue thing we said, the blue thing is the called the ground plane. The white thing are the signal paths. Signal path. The so then we have. So I'm just looking at the technical. No, okay. Then we have the signal staff. Then we have here some sort of insulation, something. They cannot touch each other, right? Insulation. And so at least this gives us one thing, which is basically that the interfere, like the magnetic fields generated by these and the ones generated by the blue layer kind of cancel each other, so there's less noise. That's one thing. Then if we look at the board like these, I think you just have to be strategic, right? I think power, obviously things depend a lot on what you're gonna have, in terms of physical requirements for the thing that you want to design the PCB for. But I would assume power should be close to a corner, right? Ideally, because if I place power here and I am assuming there's a radius of noise, right? I'm minimizing the noise that is on the board, which is just this section, right? So that's that. Then the microprocessor is going to be pretty noisy as well. It's my guess. Should be as far away as possible. So I would go in a diagonal, right? I would go in a diagonal. So that's where the microprocessor is going to be, because this is the most important part of the PCB, right? The microprocessor is what's going to do like it's the brain, right? And the same, right? So it's going to have a radius, right? And so at least you keep them as far away from each other as possible. That's the diagonal here, assuming that's the way that this looks like, right? Now the I guess in these like outside of these areas, paths can be closer to each other than in these areas. If you must put a path in here, it should probably be sort of more separated from other paths. While outside of these areas, you can go kind of closer, I guess. Right? Signal proximity and ground planes when about optimal component placement crosstalk. Um, I can't think of anything else. I can't think of anything else in here that would actually help me understand it. I think those things are. So what else could you do? I mean, position the power supply. We've positioned the power supply. We've positioned microprocessor. Diagram of the minus crosstalk. How should I place the ground plane? This is where we put the ground plane. I think just basically in here, right? So you have that canceling effect. I think that is done, and then we have the canvas tool. We have to draw a simple diagram of a PCB with components placed to minimize crosstalk, labeling potential sources of interference, such as close proximity between noisy and sensitive phrases. I think that's it, right? I mean, obviously, if you, as I said, you're gonna have um either either difference such as close proximity between noisy and sensitive. There's more noise in here. So, but I think it's basically when it comes to placing the components is consider these radius of influence of their noise. Then just position. If I were to put the third component, then I would probably put it in a place where it's the furthest away from both, and that is likely here, right? Here or here. Then once you have these, then I guess you start like, I mean, I know this is just a process to do. It's just a way to do this. Okay, so consider factors like signal proximity and ground planes when thinking about optimal. But I'm doing that already. Include a ground plane beneath the traces and label how it reduces crosstalk by providing shielding and low impedance return path when components are placed with adequate support. Include a ground plate beneath the traces. That is the ground plate here. That is the ground plate. Ground plate. Ground plate. When creating your PCB, place digital components away from analog ones. Oh, okay, interesting. Okay. And add a ground plane layer to minimize crosstalk from proximity. So why do digital and analog components have significant differences in noise profile? Yes. How do the switching behavior and current spikes of digital components compare to analog ones in terms of noise? Well, I guess analog ones are more sensitive to noise, right? Because my guess is that analog ones are more sensitive to noise. Yeah. Okay, but I mean, okay, those are within the norm of like. Those are within the norm. Looking at the at some of the commentary from the LLM that I'm. Yeah, but it's true. I mean, I need to go do some more research. I think on this. My guess is the analog ones are more sensitive to noise. I guess I need to go do some more research on these. So let's spend maybe 5 more. Let's do these. Let's do the following. Let's take so let's go find an example somewhere. Let's go find an example. Okay, now actually seems, I think when I switch the tool, it stays like that. It doesn't resize with all good. What I will do is I'm going to look for a sample so let's look for Google sample toy PCB design with 5 components, something like these images. Let's try to analyze something simple. What would be something simple? Tricks and treat. Something like these from one of these cars. I mean, that's an interesting thing here, right? Oh no, because no, I can. Let's look at some other example. Let's look for these maybe. Solar power regulator printed circuit board. One thing that catches my attention here. One thing that catches my attention. I think I deployed that, right? Yes, now I can paste image. One thing that catches my attention is that the corners are empty. And that's a bit contradicting what I was kind of saying before. It almost feels like in this design, everything is packed in the middle. Like even all the path traces are here, bro. Weird. Okay, I can see a component here. Fine. Okay, I guess it's because there's holes in here. Because usually are used to hold the board somewhere. But I'm realizing that the majority of the circuit is kind of like concentrated. I think this is power, not, yeah, this is where the power supply gets plugged in. Or these, sorry. This is power supply. Some resistors in here, some like some other ones. I think these are capacitors, I think. Yeah, and I don't know, and that's it really. There's just some like some circuits in here, but I do not, beyond placing the components far away from each other. I don't know what else am I missing. Analog ones, digital ones. This is interesting distinction. But it makes sense because they're more sensitive, right? So using a canvas tool, draw a simple diagram of PCB with a component placed to minimize crosstalk labeling potential. Let's go with something like the solar panel. Or this one even. Let's look at some of these designs. transistors, resistors, capacitors, diodes, connectors, LEDs, inductors. Here, they've done a design where you can see the microchip, like the IC thing is at the center. The components are indeed as isolated from each other as possible. Here we have, I think, some port or something. We have the support holes in the corners. And then, but it's interesting to see the capacitors essentially are grouped together, right? Using the CAN will draw a simple diagram of a PCB with the components placed to minimize crosstalk. But I think that's what I would do, right? That's so we have the board, and let's talk about this stuff. You need, on number one, you need to put components as separated from each other as possible. Okay, there are components which need more than this, right? So one is here, one component is here, and now not all of these. It seems like some components can go well with each other, like all the capacitors, like they just all, you know, seem to chill here together. Although there's another one in here, but they are compartmentalized in an area. What's interesting here is that you do see paths, but like these paths are they're also kind of grouped, but it's okay. Huh. Isn't the canvas tool a simple diagram? I guess, yeah, I don't know. I'm gonna mark this as complete. I don't know at this moment. I'll come back to this later. I don't know what else to say. I mean, I don't know also what else to minimize crosstalk, labeling potential sources of interference. Some things can be grouped, some things far away from each other, and we know for sure that certain paths should be more isolated than others if they are critical. For example, between two components. Others can be closer, etc., etc. And then at the same time, the ground plate goes underneath. Yeah, I think I'm gonna mark it as complete. I don't know why it hasn't marked it as complete. And what would be, what am I missing? What am I missing? Current path. Think back the return currents and loop areas. What is a loop areas? What single ground plane property most affects both EMI and integrity? What's EMI? What's a loop? That's a good question. Oh, it's electromagnetic interference. Okay, probably. Okay, yeah. The loop area. How does the loop area affect it? How does area So I guess, does this mean, so maybe I'm getting that wrong. Maybe I'm getting that wrong in terms of the placement of the, it radiates or peaks up a small loop versus a large one. Yeah, but I still don't understand what the loop is. Still don't understand what the loop area is. Is the area still don't understand what the loop area is. Is this the area? Why area? Is area as the occupied space of the ground plane? Oh. Imagine current living on a signal trace and returning through the ground. What area does the path enclose? But it's but the ground path is underneath signal layer, typically. Yeah, well, it's so how does the size of, how does having the return path directly underneath affect the size of the loop compared to a distant return route? It's a good question, because in terms of interference, I guess, and it's a total guess, but I guess if the trace is here, the signal path is here, and ground is here, how does the interference, well, the farther away from each other, the worse, right? Because then the interference, so this is one magnetic field, this is another one. So the farther apart from each other, the less they interfere. So I'd say the farther apart from each other, the less. Really? So the loop area increases and the ME decreases. What? I think I need to add some. I need to do a detour on electromagnetic interference here. I need to do a detour on electromagnetic interference. If the loop area increases, does that structure become a better or worse radiator? Electromagnetic loop area worse? No, better. So why do we try to keep loop area as small as possible in PCB layout? Yeah, so the interference is lower. That's what I mean. So that we're trying to keep the loop area as small as possible in PCB layout, so that there is less. Me. Yes, I can ground plane placement and continuity help achieve smaller loop area. How? By placing it right underneath. Maybe. Yes, close. In a multi-layer board, you decide where to place the ground plate relative to your signal and power layer. In between. Didn't know there's a power layer. I guess the factors that I should weigh in are where do I want to mitigate noise more, right? I mean, digital switching, power supply, and analog section. How should that guide your ground placement, plane placement? So essentially closer to analog. Closer to analog reason. Yes, how might you balance good grounding for analog areas with noise generated by digital section? Can you stack ground layers? More stack, less noise, I guess. Yes. Did I get one of these TikTok? It depends. How should multiple ground layers be positioned effectively? Should multiple ground layers be maybe on top and above signal path layers? Layers? Like alternating? What benefits and potential issues arise from sandwiching signal layers? I mean, the benefits are that no, to be honest, I don't know. You might ground planes on both sides affect the return path for it might split maybe. What would it need to do? What would you need to do to keep both ground planes working effectively as a single reference? Have them connected. I guess that will be yes. Where and how densely should they connect the multiple ground planes to each other? Where and how dense? I guess I would put those densely ground plane other bias maybe like well spread, evenly spread, stitching bias might be. How might be a spacing effect via spacing effect performance at different frequency? Okay, wait, before let's stick to these, right? I think I have to stop, guys. I'm sorry. It's been 45 minutes. I think I need to take a break. Yeah, but it's good. It's good. Technically. So I'm still stuck at step 2, which is draw a canvas tool, like draw the PCB with the components placed to minimize crosstalk, labeling potential sources of close proximity, noisy and but okay, we've learned a lot about the plan, the grounding planes. That's done. Cool. In my position, how should I route the different pairs to spacing and length? Okay, those are all interesting questions. I'm gonna stop here for now. I'm gonna pause. We'll continue. I want to spend time here because it's not, you know, what are the next steps? The next steps are consider factors like single proximity, ground plane, about optimal. We have a summary, one placement, impedance control effect, high routing. I think I might actually. So I've done okay. Let's go back to the plan. Let's go back to the piece. So this is the one we have in progress, but I think I might jump to another one. I probably will jump on to science of let's see what this one has. And I'm gonna just read the first part and then we'll stop and then go back to the other. You don't have to finish sessions, right? You like explore and then come back and it's all fine. Because we're obviously kind of stuck there. All right. So what do we have here? What is your current understanding of design rule check? The software, how they relate to manufacturability. Okay, we don't know any of that. These 3 common DRC rules. Software automatically flags violation. Summarize what I've understood so far. Okay, cool. It's more about the software piece. Perfect. But we're not starting the session. See you tomorrow, okay? Yeah, I'll keep doing some minor improvements, but I think that looks pretty good, guys. I'd almost say like go and sign up. It's just you know, kind of like a soft launch in a way. See you tomorrow. I'm gonna make a more official launch